Hey guys, welcome to part 2 of our section on 8.1. So we just finished talking about all the different cases for side-side angle, and how we can have possibly no triangle, how we could have one unique triangle, or we could even have cases where we have two potential triangles. So let's deal with a few examples dealing with side-side angle. So here we are given a triangle with A is 3, B is 2, and alpha is 40 degrees. So if we go back up to our chart, we have that alpha is 40 degrees, and A is 3, and B is 2. So we have that alpha is acute, so we're in one of these first four cases. Oh, I didn't put an E on here. Acute. And A is greater than or equal to B, which is what we have here, because A is 3, B is 2. So that means if A is acute, if the measure of angle alpha is acute, and A is greater than or equal to B, there's one unique triangle. Awesome. So that tells me here that there is one unique triangle that satisfies this. This is our angle A, which is our alpha, which is our 40 degrees. Side B, which is 2. Side A, which equals 3. So we need to find what C is, gamma is, and what beta is. And we can do this just exactly the same way we have the rest of the examples. Let's find, sorry, this isn't exactly the same. This is slightly different. We need to find one of these two angles first, because we don't know either C or gamma, so we can't do anything with that. And I know what little b is, but I don't know what beta is. So I'm trying to find beta. And so since I'm trying to find beta, I want to use the set of equations for law sines where beta is in the numerator, or unknown. And so what we end up with is a slightly different expression where we have sine of beta over 2 equals sine of 40 degrees over 3. So multiply both sides by 2. And we get sine of beta is 2 sine 40 degrees over 3. And so then we can use inverse sine functions. Since our beta we know is going to be an acute angle, even if it's obtuse, right, this would still kind of work out for us. We can figure this out. But so we just use inverse sine features. So we have inverse sine. Actually, you know what? Instead of doing it like that, I'm just going to go ahead and write. So beta is equal to the inverse sine of 2 times the sine of 40 degrees all over 3. And so what we then do is we just use our calculator, making sure you're in the correct mode, right? We need to be in degree mode. So make sure that you guys are there. Inverse sine of 2 sine of 40 degrees over 3. And we get that beta is approximately 25.37 degrees. And so what we do from there is we use our very simple fact that the angles of a triangle add up to 180. So we get that gamma is equal to 180 minus 40 minus 25.37. To get that gamma is equal to 180 minus 40 minus 25.37. We get 114.63 degrees. Now we know gamma, so now we can do things the way we've done them, and we get an expression of C over sine of 114.63 degrees equals 3 over sine of 40 degrees. I don't know why I put that in parentheses. Multiply both sides, and we end up with a nice C equals 3 times sine of 114.63 degrees over sine of 40 degrees. And so C is approximately 3 times sine of 114.63 over sine of 40. We get that C approximately 4.24 degrees. There you have it. We have beta, we have C, we have gamma. Now, what if we have the case where we have A is equal to 1, B is equal to 2, and A, our measure of angle A, is 50 degrees. So A is acute. So we come up to our table, right? We look at that. So we're not in those last two. So we know that A is acute. And what I know is that little a is 1 and little b is 2. So I'm not in this second case. And so what I need to figure out, if you look at the other cases, it's all about the relationship to h. If a is less than h, then we have no possible triangles. If a is equal to h, we have one triangle. And if a is greater than h, we have two triangles. Right? The reason why I can kind of ignore this part is because we already said that a is less than b, right? Because a is 1, b is 2. So we've already established that a is less than b. So that means we're not here. So we're not in the second case. And this is already satisfied. So it depends on if a is less than h, equal to h, or greater than h. So let's find what h is. How do we do that? Well, what I know, I'm just going to draw this arbitrarily. I don't know if this is actually how it looks or not. Okay. I know that this angle here is 50 degrees. This side here is B, and we're going to say that and that's 2, and this is A is 1. I want to find H. And the way we do that is we essentially ignore the side A and the rest of that right-hand side of the triangle and treat it as the right triangle with an angle 50 degrees, a length of H, and a hypotenuse of 2. And so what that gives me is it gives me the equation sine of 50 degrees is H over 2. Multiply both sides by 2. And we get that 2 sine of 50 degrees equals H. So we get that H is approximately 2 sine of 50, 1.53. So if H is approximately 1.53, A is 1, so that means that our angle A is acute, and our side A is less than H, so that means we have no possible triangles. So you would say that there is no possible triangle. You could simply say something like no solution. You could say something like does not exist, right? Answer this based on what the problem is telling you to give as an answer. So like on the online homework, if it says if the triangle doesn't exist, enter D and E for all of them, enter D and E for all of them, right? Do what it says. If this is a paper test or anything like that, or just a fill in the blank kind of thing, just no possible triangle, no solution, D and E, any one of those three would be fine for my purposes. If the problem specifically states what to say that. Otherwise, any of these three will work. Let's look at example 6. We're still doing our side-side angle. So again, we have the acute alpha. We have that B is greater than A. So we need to figure out what H is. So this is exactly the same idea as 5. Depending on whether A is less than H, equal to H, or greater than H, we'll either have no possible triangles, one possible triangle, or two possible triangles. And so we need to figure out what H is. And so what we do is we start with our angle here of 35 degrees. We start with our side B here, which is 8. I'm going to give myself a little more room here. There we go. Our side H, side B is 8. Our angle here is 35 degrees. So we know that sine 35 degrees is equal to H over 8. So we get very simply that H to 8 sine of 35 degrees. And if we get the approximation for that, we get 4.6. So we have that H is less than A is less than B. That means that we have 2 possible triangles. Which means A could go either one of these routes. So what I want to do is I want to create 2 separate problems, 2 separate triangles. So we've got this triangle here. That's 35. That's 8. That's 6. And then we've got this triangle again, 35, 8, and 6. And so what we're going to do is we're going to label these triangles. So we'll label this angle here beta 1, gamma 1. I'm running out of room. I am going to draw these a little bit bigger, give myself a little more room. Make this work. I don't know why I keep drawing equilateral triangles. It bothers me. You guys probably don't care. There. Okay, so this is our 35 degrees, 8, 6, beta 1, gamma 1, C1. Okay. Now, the reason I put these sub 1s is because this is just our first potential triangle. Here's our other triangle, 35, 8, 6. And this is beta 2, gamma 2, and C2. And so what we're going to do is I'm going to take kind of zoom out a little bit so we have a little more of an overall view. There we go. Let's split this page in half. Our left side will do triangle 1, right side will do triangle 2. So given this triangle, we need to, just like we did on this last example here, or sorry, not that one, on example 4, we first have to find one of the angles using the law of sines. And so it doesn't really matter kind of which triangle you want to start with, which one's B1, which one's B2. I have them labeled this way because this is the way I have them labeled. You can absolutely do other ways too. So we're going to round to 1 decimal place just because I'm running low on room and I want to keep things a little bit simpler as much as I can, save every second I can. Because I need to find the angle, I want the angles on top. So I'm going to look for beta 1 first. And the only reason is because I know what little b is. So we get sine of beta 1 over 8 is equal to sine of 35 degrees over 6. So skipping some steps, so multiplying by 8, then taking the inverse of both sides, we get inverse sine is equal to 8 times, or sorry, beta 1 is equal to the inverse sine of 8 times sine of 35 degrees all over 6. So beta 1 is approximately equal to 49.9 degrees. Okay. So from there, get that gamma 1 is 180 degrees minus 35 degrees minus 49.9 degrees. So gamma 1, 95.1. Now all that's left is to find C. So we get that C over sine of 95.1 degrees. 1 degrees is equal to, and again, we want to use the side that we know are side pairings, side and angle pairings that we know the exact values of. So we use 6 and 35. So 6 over 35 over sine 35 degrees. So we end up with C equals 6 times the sine of 95.1 degrees over the sine of 35 degrees, which is approximately equal to 10.4 degrees. Or sorry, 10.4, not 10.4 degrees. And if we come back up to our triangle, that makes sense. Even though this isn't to scale, C definitely looks to be the longest side. Now, let's move over to our triangle 2. Again, we need to figure out, basically, we're doing the exact same thing that we did on this other one. But the difference here, okay, hang on one second. Sorry, my brain just checked out for a minute. Oh, there we go. Now I remember. I was trying to remember how my explanation of this. So when we have the two case situation, it's relies on this very kind of nice geometry property. Okay. So basically, what we have, I don't want to go into the geometry of it for you. What we end up with is once we have beta 1, we can find. I don't like these guys. I don't do these cases very often for you guys because they're just annoying. There's a couple formulas and stuff like that. You know what? I'm just going to go ahead and throw this out here. And I'm going to tell you guys, don't worry about this. I'm not going to give you these problems. I'm just going to show it to you. So basically, there's a few conditions that we can meet. If you look in the textbook, there's a solving the ambiguous case, and there's a two solutions situation. It gives us basically a nice if alpha plus plus beta 2 is less than 180 degrees. There's two triangles. It's just the two triangle thing that we've already figured out a different way, a better way. So then we say gamma 1 equals, we already figured that out. Why is this giving me fits? I'm so sorry. This is very terrible of me. There we go. Beta 2 is equal to 180 minus beta 1. Wow, that was terrible. I'm so sorry about that. I don't want to go through the derivation of it. That's why I was trying to look through my notes for the end formula, getting through all the derivation. I don't want to do the derivation of this because, quite frankly, you don't care. I don't care. It's not something you're going to need to know for this class, for any other class for that matter. So we have this lovely little thing right here. Okay. So we know what beta 1 was. Beta 1 was 49.9 degrees. That means beta 2 is 180 degrees minus 49.9 degrees, which is equal to 130.1 degrees. So that's our beta 2. So that means that gamma 2 is equal to 180 minus 35 degrees minus 130.1 degrees. So gamma 2 equals 14.9 degrees. All right. So sorry about that whole mishap and my brain just not firing correctly. We can now go through and figure out our value for C because we know our two angles. This is a really quick, easy problem. Set up the exact same way as we did before. C2 over sine of gamma 2, in this case 14.9 degrees, is equal to R6 over sine of 35 degrees. So C2 equals 6 sine of 14.9 degrees over sine of 35 degrees. Means C2 is approximately 2.7. Okay. See, even these problems mess my brain up sometimes. There's just a lot going on with these kind of problems. So I really want you to take it slow. Big thing to key on, and this might be something you want to go back and put in here. The only time we have two possible things right in here that beta 2 equals 180 degrees minus beta 1. It doesn't matter which one's beta 1, which one's beta 2, right? It's all going to come out to be the same thing. This really just comes to kind of a parallel line, reflective angle, kind of ideas and identity here. Nothing crazy. Okay. If you want to know more about it, want to know how that works, how this 180 minus beta 1 is beta 2, feel free to shoot me a message and we can absolutely go through it. But I don't want to take any more of your time to do it on here. So, area of triangles. Area of triangles is really easy. It's a very nice, simple formula. The area of a triangle, so if we were given some arbitrary triangle, height h, and some base length b, that the area, I'm going to not do red for this, that the area is equal to 1/2 base times height. That's really easy. But what if I know this here is alpha. This is going to be tricky. So that's still base. Oh, you know what? I'm just going to leave that. Okay. So that's just general. But what if we have some triangle in the standard position, alpha, beta, gamma, C, B, A, and we have this height here. Well, to find the area of this triangle, I need to know the height. If I use kind of what we did at the very, very beginning, we get that the height is equal to B times the sine of alpha. But we can also get that the height is equal to C sine of beta, or A sine of gamma. All of those are the same. So what we can do with this is we can create essentially three different equations depending on what we know for the area of a triangle. The area is equal to 1/2 B times C sine of alpha, 1/2 A wait, what? My notes. Sorry, there's something wrong with my notes. Now I'm annoying myself. I apologize. A times B. Why am I just? I am so sorry. You know what? Clearly, I'm having a great night. Let's just focus on this specific example here. And we'll figure this all out together because apparently my brain does not want to work. So we have that A is 30, B is 6, and C is 8. So we do not have side-side angle. Okay. What we have is side, angle, side. And so if we create this triangle, we have our angle A here, which is 30 degrees. Side B is 6, side C is 8. So here's an A, beta, gamma. To figure out the okay. Yeah. I figured out my brain. I'm so sorry, guys. Areas of triangles. 1/2 BC sine alpha, 1/2 AC sine beta, and 1/2 AB sine gamma. Okay, notice all three are used letters, kind of if you imagine alpha being A, beta being B, gamma being C. So we need to have two of the sides and the angle between them is what we need. And so we can do that like this. And so here we know C, we know B, and we know alpha. So that means the area of this triangle is 1/2 6 times 8 times sine of 30 degrees. And so we just punch that into our calculator. Okay. And sine of 30 degrees, that's a nice special number, isn't it? That's just 1/2. So 1/2 6 times 8 gives us 24. Sine of 30 is that special one, 1/2. That means the area is 12. And then we want to be big, extra fancy mathematicians. So 12 square units. All right. I am sorry about my brain misfiring on this video. We'll get it better next time. But hey, I'm a teacher. I'm not a perfect person. Neither should you be. So let's do this together. All right, you guys. That's the end of this video. Thankfully, we are done. Have a great time, and I'll see you guys for 8.2.